Hey there! In this tutorial I will show you how to create this kind of 3D truss using a Grasshopper script. In order to understand completely my presentation, you need to have a basic understanding of data trees in Grasshopper, and also you need to understand how to handle lists, collections in general. I will start from telling you about the main assumptions and the main guidelines that we have to follow when we create this kind of structure. And then I will start with a blank script and explain whatever I'm doing. By the way, if you want to learn whatever I'm showing here, you should watch this tutorial, try to understand it, maybe take some notes. Whenever you don't understand completely what I'm doing, maybe you should pause for a second and just try to think about it. But after you finish, you should try to do exactly the same on your own without any help, just to make sure that you grasped the techniques that I'm showing here. Without trying such exercises on your own, you might have hard times learning this kind of material. So this 3D truss bases on a freeform surface. I will show you it's here in the Rhino file. So what I'm doing is I reference this freeform surface to my script, and then I assume that whatever is generated by Grasshopper has to be, well, let's say, easy to manufacture. So the problem with freeform surfaces is that they are often doubly curved, which means that they have a curvature in both directions, and this is extremely difficult to fabricate. So we often try to tessellate such forms to obtain shapes that are easier to manufacture. And one of those shapes is a triangle. A triangle is always planar, it's always flat, so it is very easy to cut it out from a piece of glass or piece of metal or any other material, really. So in this tutorial I will show you how to tessel, how to create a surface from triangles out of a freeform surface. That's one thing. And then how to create this kind of substructure which is bearing the loads from this glass. Of course, this is fully parametric. I don't know what you can argue what fully means. I will turn off some of the previous just for that to calculate faster. All the fancy three-dimensional struts and so on. We don't really need that. Okay, so here we are. Just a linear model will work much faster. So it is parametric in that way that I can easily pick a number of divisions in both directions. This is a matter of resolution, so the less panels I have, the less precise this representation will be. So that's one thing. I think that the only other significant parameter is the height of the truss. So it lets you control, let's say, the thickness of the structure. I think that in reality it would affect the physical properties of this structure. Probably it would be stronger if the truss was higher, but it will also take more material. Doesn't matter really. So as I said, we start from a freeform surface. Once again, I will show you that it's in the file. Of course, I could remodel it just to show you how you can control the structure by dragging the geometry in Rhino. I also like to compose my scripts so that they have some kind of input that is interactive. By what I mean, that you can control some things in your Grasshopper scripts not only by dragging sliders and changing values, but also by changing the geometry that is the base for your algorithms. So as you can see, this is fully interactive, works well, and this is our aim. So a freeform structure, triangular panels on the top, and a linear substructure. So every field, every panel is supported by 4 struts, and the tips of those pyramids, let's say, they are connected into a grid as well to form the secondary rows of struts to keep this all stable in all directions. Yeah, so let's start over. I'm opening a new file. I will probably use the same surface as before. So as I said, first thing that we need to do every time, reference any geometry that will be base of our script, in this case the surface. Every time I reference something, I usually turn the preview off in Rhino so that I don't have any intersecting surfaces. Just spoils the preview. And now the first thing that we need to do, obviously, is to divide the surface into smaller pieces. So I will use the technique that I showed you before. So we have a surface, and then we will use iso trim component, and along the iso trim we also need to divide the main, divide it to the two-dimensional domain. Of course, 2 values for the number of divisions, 2 sliders with integral values. And yeah, I will do what I usually do. So I will use the surface. I will put it in the domain input. You just need to understand that the surface is converted to its parametric domain when you do something like that. I think that I will reparameterize the surface anyway. So its domain will be normalized, and then these are the segments, and this is the surface. Once again, this is we have two geometries in the same place, so this is why the preview looks like that. So I will turn off the preview for everything that is not required for me to work, and as you can see, I can just divide the surface into panels. The problem is that those panels are still freeform, so they are curved in both directions. As I said before, well, most of the times it's difficult to manufacture, so it would be much easier if we converted those into triangular panels. So this is the first thing that we will do. So I will close that group. So this is yeah, that's my group, and I would call it the first group divide surface. And I think that I also need to put those values somewhere, or to emphasize that these settings are global, because I think that I will use the number of divisions elsewhere in the script. So let's call that U divisions and the other V divisions, or V division count, whatever. And this could be grouped in a blue group. As you know, I like to color code my groups, and I usually use blue groups for the input. Pale blue doesn't matter, honestly. Okay, so we divided the surface. Now let's find a way to convert all those panels into triangles. You probably know my way of organizing the scripts, which is to enclose all significant procedures into such groups where I have input and output, and this is why I'm copying these data containers. I just want to keep everything clean, so I will call that panels. And now how to convert all the panels into triangles. So we start from a freeform shape, whatever it is, but we know that it has 4 vertices. As you know, the indexing starts from 0. This is why I marked the first vertex as 0. So we have vertex 0, then vertex with index 1, then vertex with index 2, then vertex with index 3. And now the question is how we can convert such information if we know that we can extract vertices, how we can convert that into triangular panels, into flat triangular panels. So obviously we would need to create a triangle from 2 triplets. We would need to create 2 triangles from 2 triplets of vertices. So let's say that I would take vertex, once again, vertex with index 3, vertex with index 0, and then vertex with index 1, and form a triangle from those 3. And then take vertex index 1, vertex index 2, and vertex index 3, and create another triangle. And this is actually what we will do. So we will create 2 surfaces. Out of each panel, we will create 2 surfaces where both of them will be flat surfaces using only 3 of vertices of the panel. So I will maybe move it somewhere. I will delete it later because it's not a pretty sketch. So we have a panel. Now, how do we get vertices? There is a component which is called deconstruct brep, and we can deconstruct the brep. It gives us faces. The faces are basically, in this case, we have 1 face per each brep because this is just a surface. Then we have edges. Again, for such rectangular surfaces, we get 4 edges per panel and also 4 vertices per panel. By the way, you should notice that what we get from this component is a data tree. So I input 99 breps. Probably I could reduce this number to make it clearer. Anyway, we get 99 surfaces, 99 breps, and this data is branching out into a data tree which has 99 branches, and every branch contains only edges of the panel that it was made from. So if you take a branch with index 40, then it will contain a list of 4 edges, and these 4 edges belong to brep that was provided here as a brep with index 40. So this is how it works. Actually, for this group, you don't really need to understand all that. So you can just take the vertices, like let's use list item list item component to see what is happening. So if I take list item with its default value, so it takes index 0, you will notice that I get a single point per each branch. And this is basically how this item works with data trees. So it gets me nth element from each branch. So in this case, I will get the first vertex from every panel. So I get this one. But if I zoom into this component, I can increase the number of outputs. So I get vertex 0, vertex 1, vertex 2, and vertex 3. Which allows me to easily create those triangles. How? There is another component which might help us here. It's called surface 4-point surface. Yes, it's here, 4-point surface. And you can either provide, if you read the description of this component, you can see that you can either create a surface that connects 3 or 4 corner points. So let's see. I will use the first one, the second one, and the third one. So actually I created the triangle from 0, 1, and 2. Not like in this drawing, but still it works. So if we turn off the preview of everything before, to just have the 4-point surface that we just created, so corner A, corner B, and corner C, we get those nice flat triangles. Again, why does it work? Because we provide a single point, like here in corner A, we provide 99 first corners from those 99 B-reps. Then we provide only the first corner from every panel and only the second corner. So now I will use the same component again. So 4-point surface again, and let's try to make the other triangle. So I used 0, 1, and 2. Now let's use 2, 3, and 0. So again, 2, 3, and 0, and it gives us the other triangle. So I would say that we're done with this group. We could add some more detail, like we could scale those panels a little, or we could add pipes around the edges, but actually the most important part is done. So let's close this group. I would actually merge those two data streams and output the result as one data tree. Maybe simplified. You remember, probably remember that when you simplify a data tree, you can compare the structures of what's going out from the merge component and what goes out from the surface component at the moment. The surface is simplified. So if you compare those two, you can see that simplification removes the redundant indices from data tree's paths. So here I have 2 zeros at the beginning of each path, but they are shared among all paths, so this is redundant. We don't need those to differentiate between paths. So when you simplify the structure, you get only branches with nice clean paths. The paths are in the curly braces. Okay, let's call that triangular panels, and I would close this group. Or instead of create triangular panels, I would just call it triangulate surface. Okay, and well, we're halfway through. So the next step and the next thing that we need to do is in a similar way as we did before. So before we were thinking of getting a single panel and then converting that to triangles, and in the same way we need to think of how we can introduce this substructure for every panel separately. So this is what we get. Again, we will get a surface and we will get 4 vertices. And I don't know if you remember, but the substructure was formed in a way that a center point of this panel was given or found, and then it was translated beneath the panel, and the vertices connected to that moved point. So this formed a kind of pyramid. But this is another, maybe a little more difficult task. A more difficult task is to connect those pyramids, so-called pyramids, from different panels. So let's say that we have more than one panel, and then we want to connect them together with a grid below, but that's a different story. So let's start from creating those simple pyramids. So we need to create a line between every vertex of every panel with the center of that panel, with the center. So again, this is a separate group, so we'll start for a new one also with just the panel inputs. And again, we need to deconstruct brep. I know that we already deconstructed those panels, but let's we can repeat that. This is not a very computationally heavy operation, so we can just for the sake of readability, we can copy that as well. So, okay, we get the vertices per each panel, just as we did before. So it's a data tree. So let's leave it for now. And now let's find the center point of each of the panels. For this, I will use evaluate surface. You could also use area, but area is somehow slow when you are finding a centroid of a freeform surface. So yeah, I will use evaluate surface just also to remind you how it works. So here you need to provide the surface, and then you need to provide UV coordinates on that surface, and you will get a point. So there are many ways to do that. You can use MD slider with default values. It will give you point at half. Of course, you need to normalize the surface first, so you need to reparameterize it here. So this is one way of creating a point at half and half units. Of course, you can just type in 0.5 and 0.5 in a panel. You could use construct points. There are just many ways of doing the same thing. In Grasshopper, you just need to find the one that is like, let's say, yours. You need to find your method. I would personally use a panel with constant value typed like this, because I don't want anyone to actually move around such sliders and see what is happening. I also don't suppose that this might be a subject of any kind of optimization. I don't know that. I don't think that changing the center of this a cell of substructure might affect the resistance anyhow in a positive way. So let's just use the panel, half and a half, and now we need to move them downwards. So of course I said downwards, so you can interpret that in different ways, because so let's assume that we have a surface like that, and you have the surface a point in its surface. And now what does downwards mean? Does it mean in a reverse direction than the z-axis? So would it be like translated like that? Or downwards means relative or by reverse normal vector of the surface at the center point? So that's something that you should probably answer. I think that in our case, a more flexible and better approach would be to use a reversed normal vector, because I don't know, let's imagine that we are creating a this kind of truss for, I don't know, a wall, or I suppose the roof couldn't have this kind of shape. However, such substructure looks more sensible to me than if those points were just translated along the z-axis. So let's use a reversed normal direction. So we have the normal vector here. We will need the parameter. I will call that height of the truss or substructure, and then a sensible range of values. Actually, this is not sensible, because what would be 5 centimeters, 5 meters? I think that both values are irrelevant. So yeah, let's leave it like that. It's just in scale of this model, which is not in scale at all. So amplitude, I'm using the normal vector, but I'm changing its amplitude, and I use the resulting vector to move the points. Now, as you can see, they are moving upwards because the normal vector is pointing up. This is where the front or the top of the surface is. So I would need to change this to a negative value, or just use a reverse vector components. Doesn't matter, really. But okay, here we are. So we have the points and they are center points. And we also have the vertices of every panel. So now let's just connect them and see what happens. Connect them with a line. So this is the end point and this is the start point. And I suppose that this is not something that you would expect to see. So what happens? Here we have all the center points that are translated downwards. Here, pay attention to how those data structures look like. So this is those center points are just a plain list. So this is just a list, and here in start point, we input a data tree. So a data tree is a collection of lists. So this is a list of lists. It actually contains 99 lists, but here we input a single list. You probably remember when I mentioned that that lacing has, let's say, two rounds. So in the first round of lacing is how the data is combined in Grasshopper. In the first round, you combine list to list, and the second round is the one that you are used to, is the item. Sorry, I cannot write item to item. So in our case, the first round of lacing assigned, so per each branch from this data tree, which we have 99 branches, at least I have that many, because this is how many panels I have. So every branch was assigned to this whole list. So every 4 points from those, so every 4 vertices were connected with all 99 center points of the structure. So once again, let's see. So these are my branches on the first input, and this is the list of so these are start points, and these are end points, and we have 99 points here, and we have 4 points on each of those branches, and so on. So in the first round of lacing, this is what happened. So every list that contained 4 points was connected with another list that contained 99 points. So this is that first round of lacing. And then in the second round, every 4 corners, so we have 4 items on one list and 99 items on the other. So in the second round of lacing, the first corner was connected to the first center point, the second to the second, third to third, fourth to fourth, and then fourth was connected with all the other points on that huge 99 element list. Second round of lacing. So this is basically what happened, and this is one of the most common errors that you might make when you're creating your scripts, and it often costs you time, because you need to restart your file. At least you need to go back to the last autosave. So as I said, the common mistake that you might make is to combine a data tree with a list without really knowing what you are doing, because this will multiply the number of items that you get as the output. As you can see here, I got almost 10,000 lines. So you can just imagine what would happen if these were not lightweight lines, but if they were, I don't know, 3D pipes. I suppose that my computer would calculate it for 15-20 seconds or something like that. So you have to always be aware and attentive when it comes to different data structures, So whenever you connect a data tree, which is represented by this dashed line, with a list, which is represented by just a thick wire, you need to think twice about what is happening. And now the simple solution to this problem is just to convert that list to a data tree by grafting. You graft the easiest way, and I think that the only good way to graft, of course, there is a component which is called grafts. I showed it to you before. You right click on one of the outputs and you click on graft, and now the problem is solved almost magically. But let's think about what has just happened. So here we have 99 branches, and graft converted it converted the list into 99 separate branches, from which all contain just a single element. This is the story that I told you about, those expensive apples that are all packed in a single piece of paper. So instead of having those 99 elements on a list, we decided to put every item separately its own bag, let's say, quotation marks. So these are all separate bags or separate lists, which changed the behavior that occurred in the first round of lacing. Because instead of having a single list of 99 elements, we now have 99 lists from which all contain a single element. So, and now those two data streams, they are compatible, let's say. So we have the same number of branches on the first tree as we have on the other tree. So each branch will be combined with its pair on the other. And then the second round of lacing will look much better. So we just have 4 points and just 1 point on the other branch. And, all those corner points will be connected to the one in the middle. If you have problems understanding that, then try to, write it for yourself on paper. Just spend a while thinking of what is happening here and why it worked in my case. Okay, so these are I would call maybe primary struts. I will leave those as a data tree. So we have 99 branches, each of them. So we have a branch per each panel, and each of them contains four struts. I will simplify that to clean up the indices. Turn off the preview. And now the other, maybe a little more difficult task. How can we create connections between those tips, those vertices? How can we do that? So we have them here. Here. And let's just connect them with a polyline. Polyline. Of course, this won't work because polyline works on a list of vertices, and now I input 99 list where each contain just a single vertex, and you simply cannot create a polyline from a single vertex. So we'll get 99 empty polylines. So let's try to flatten that. Flattening, on the other hand, it's the opposite of grafting. So instead of putting putting every item from a list on its own branch, flattening is putting all branches on a single list. So right now I have a list of 99 elements, so this polyline will have 99 vertices, and it almost looks good, but I have these unwanted connections on the, let's say, diagonals or between columns of points, because this row of points is connected properly, how I would expect it to connect. then we have the second, the third, and so on. But I don't want these connections, certainly. So what I will do here is, instead of flattening, sorry, 0 points. So I will flatten, sorry, not instead of flattening, but I will flatten that, and then I will partition it into rows of points. So let's count how many points do we have in a single row. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there is a component which is called partition list, and I counted 11 vertices. It might be different on your computers, and let's see how this works. Of course, turn off flattening here. Okay, it works well in my case. Partition list is a component which converts a flat list of points into a data tree by splitting the list into chunks, which means that for exactly, this is like this icon. So let's say that I have a number of elements, number of items, and then I want to partition that into a data tree. And let's say that I choose to partition for every 4 elements. So I take first 4 elements and I put them on branch 0. Then I take the next 4 elements and I put them on branch with index 1. And then we just have 2 rest elements and they will land on the last branch too. So this is how partition list works, and it is very useful, especially in such case where I have a flat list of vertices and I just need to divide them into rows like that to connect them all with polyline. Okay, but there is a question how to connect them in the other direction. And now the other component that you might remember already will be useful, but let's first use point list to visualize how this data tree, how this partitioned list looks like. So instead of having points, I will quickly swap the wires here. So I put the flat list to point list. You see that I have these points are just on a single list, and they have the indices are increased, let's say, linearly. And then after partitioning, I get I don't even know how many, 9 rows, and each of the rows contains 11 points. So the polyline component connects connects all points that are on the same list. So these are those, and they are displayed, distinguished by different colors. And now we would like to connect not rows but connect columns together. And you remember that component flip matrix actually allows us to do that. It flips rows and columns. If you put that into point list component, then you will see that all the points that share 0 index, they are put on the same branch. The same applies to points that share index 1 and so on. So this just collects all items that share the same index. And if I use polyline after I flip the matrix, I will get the connections in the other direction. Okay, so it looks like we are almost finished, but now there is one thing that we need to solve, certainly, and this is this hard-coded value. Because I counted 11 as the number of points in a single row, but I can change this value. And now the question is, will it be still valid? And the answer is no. So we need to think where this value 11 comes from. And actually, this is the answer. You probably noticed that when I was changing U divisions, the number of divisions in U direction, nothing has changed, and it was always divided nicely. But when I changed the number of divisions in the other direction, it broke, which means that this 11 or you can intuitively say that the way that these segments in the divide service are organized is that you have chunks where each chunk has 11 has v number of elements, and you can actually see that clearly when you look at the domains that come from divide domain component. You can see that there are pieces of, these domains share the same U span while these are changing, and you will have that many repetitions here, as many divisions you have in the v direction. And actually this is one of the chunks, so this is one of rows that we generated later. So all that we need to do is to replace this value. Actually, we could call it the v division count. It could be also a number, like an integer data container, but you can just plug it like that. So v divisions goes here. It will work fine as well. So 11. And now whenever I'm changing that, this value is changing as well, and I get different chunks of the data tree. And now I think that this is the solution. Yep. So I will leave adding additional details to you if you want to make this all look more interesting. Then you can of course add pipes, add a material to these panels, and so on. But in general, the main logic is here. So thanks for watching, and right now try to do the same. So try to create the same script, but without picking at my hints or without looking at into any of your materials. Thanks, and see you next time.